Yes, ma'am.
Okay, fine. See, we have done these two types of forces, force of cohesion and force of adhesion. If the force of attraction is between the molecule of same substances, then we call that particular force as cohesive force or force of cohesion. For example, the force between water-water molecules. Then we have seen force of attraction between molecules of two different substances. That force is known as adhesive force or force of adhesion. For example, glass water molecules. If you take water in a glass and you invert the glass, then some water molecules will be left inside the glass. Water molecules will stick to the surface of glass. Why would they stick? Is because the adhesive force is greater than the cohesive force. That's why the liquid tends to wet the walls of the container. For example, in case of water and glass. But if reverse happens, if the cohesive force is greater than adhesive force, then the liquid will not wet completely. For example, mercury in glass. If mercury is taken, then all the mercury comes out as a continuous. Now see, next phenomena we have is known as surface tension. It is based on these forces only. The molecules of liquid attract each other. I draw a vessel. And I have filled it with a liquid. So the molecules of the liquid attract each other. Otherwise, the liquid would not have a definite volume. So if the molecules attract each other, what happens is that the water molecule, let's say this is A and this is B. Fine. So these are the two water molecules. For example, I have taken. So the water molecule A is attracted by the water molecule from all sides, from all the sides. Similarly, water molecule B is also attracted from all the sides. Now what happened? There is a net downward molecular force on this A molecule. So this is a result of the surface of a liquid. What happens is that the surface of a liquid behaves as a stretched membrane. And because of the tension, under tension, and tries to occupy as small area as possible is called free surface. See, I'll let you know what does this mean. What happens is that the result is the surface of a liquid behaving as a stretched membrane, the free surface of water, or the liquid acts as a stretched membrane. In other words, you can simply say that the attractive intermolecular forces on the surface of the liquid, whatever is the attractive intermolecular forces. Why are they attractive? Because the molecules tend to attract each other. So the attractive intermolecular forces on the surface of the liquid tends to compress the liquid. That is, you can say liquid tries to minimize in surface area. Minimize its surface area. So this effect is what is known as surface tension. The property of a liquid at rest by virtue of which its free surface behaves like a stretched membrane. This is the free surface of the liquid under tension and tries to occupy as small area as possible. It tends to minimize its surface area. So this phenomena is known as surface tension. The molecules on the surface of the liquid have more potential energy than those within the liquid. So it is because to take the molecules from the interior of the liquid to the surface. So work is done. So that we'll see later on. Surface energy is the phenomena. But for now, property of liquid at rest by virtue of its free surface behaves like a stretched membrane under tension and tries to occupy small area as possible is known as surface tension. You can see the examples from your daily life. You've seen those paint brushes that we have. The edge of the paint brushes is like this when it is kept in air. And when you insert it into water, all the bristles separate out like this. And when you take it out back in air again, it becomes like this, the surface of the paintbrush. So what happens for a given volume, this paintbrush sphere has to attain its minimum surface area. So every surface of a liquid tries to become spherical. So that's what happens. That's why when you take the brush out, this is the case for water, or for the fluid or the liquid, you can say. This is the case for air. You must have seen this. When you take a paintbrush, the edge or the tips of the paintbrushes are together. They are stuck together. But when a dry brush is dipped in water, its hair spread out. So when your camel hair brush is dipped in water, the hair spread out. When the brush is removed from water, its hair clings together. So the reason is simple. When the brush is in water, there is water all around its hair. Consequently, there is no free surface, and the effect of surface tension is absent over here. When the brush is taken out of water, the forces of tension contract the hair. Understood? Is it clear till here? Or you can say, you can take another example of the eliminating effects of gravity. Soap bubbles are almost perfect spheres because they have large surface area and negligible masses. So you can say effect of gravity is almost nil. So a drop of oil is left gently in a mixture, and of spirit and water. You must have seen if you keep the drop in water, it separates. So this is because these are all the applications of the phenomena known as surface tension. So just note the definition, then we'll see the molecular theory of surface tension.
Done, ma'am.
So again, I'm repeating. Every system tends to arrange itself in a way that it has minimum potential energy. So the free surface of the liquid also tends to have minimum potential energy. So this is only possible if the area of the liquid surface is minimum. So in order to acquire the minimum area, the surface of the liquid tends to contract and hence behaves as a stretched membrane. So you can say the attractive intermolecular forces on the surface of liquid tends to compress the liquid surface. So liquid tries to minimize in its surface area, and that phenomena is known as surface tension. Now calculation of surface tension, how do we calculate it? It is a physical quantity which is equal to force per unit length on an imaginary line drawn on free surface of liquid. So the formula for surface tension is force per unit length. Force per unit length. And a length is the length of the free surface that we have been referring to. Length of the free surface. Oh, no, it is the force. And surface tension is a scalar quantity. Okay, can you tell its SI unit if the formula is given to you? Formula is force per unit length. What should be the SI unit?
Newton per meter.
Newton per meter, yes. Newton per meter. Its SI unit is Newton per meter. You can say in CGS it would be dyne per centimeter. Just note this down as well.
Done, ma'am.
See, the question over here says that a dust particle of mass m remains in equilibrium over a liquid film of length L. You have to find out surface tension. See, it's like a dust particle is over here, and the mass of dust particle is m, and it is in equilibrium over a liquid film of length L. Now see, if it is written liquid film, this means soap film, and soap film has double area. So total length for a soap film is double. Remember this point. Total length of soap film is not only L, it's double of the length of the film. Just in case of soap film. For other film or for other liquid surfaces, it's length only. Now tell me if this is length L. L is the length for this soap film, and here is the soap. So can you tell me what is the force acting on this dust particle?
mg.
Mg. Mg will act in the downward direction. Mg will be acting in the downward direction. So if F is the force acting on it and Mg is in downward direction, it says that the particle remains in equilibrium. So this means F is equal to Mg. Now force, if S is, okay, we have to calculate out the surface tension. Now see, force of the free surface is equal to actually the weight of drop. So force on the free surface is equal to, what is mg? Mg is the weight of drop. Yes or no? Now see, surface tension. What should be the formula for surface tension? You've just seen.
Force by length.
So it would be F by L.
Yes.
No, see, in case of soap film, the total length is now 2L. So the surface tension would be F by L for a soap film. It would be F by 2L. And what is F equal to? Mg? Yes, is the force equal to mg? So surface tension, can I write surface tension as mg divided by 2L? So this gives us the value of the surface tension. Just note this down.
Done, ma'am.
Both of you? Yes,
Yes, ma'am.
Aisha? Okay. See, do one more question based on this and note these points as well. These 3 points are important points there, and try this question as well. And both of you send me your answers in the chat box. Aisha, you also participate. Try this question, send your answer in the chat box. See, the question says that a wire ring of 3 centimeter radius, means if this is the wire ring, then the radius is 3 centimeters. It is rested on the surface of a liquid and then raised. The pull required is 3.03 grams to break the film. We have to find out the surface tension for liquid. So again, the force will be equal to the gravitational force, mg, because it says that it is resting on the surface of a liquid and then raised, and the pull required is this much mass to break the film. So it means that in the downwards direction, weight will be acting. The force will be force due to surface tension is equal to the weight. Force due to surface tension is equal to the weight, is equal to the weight. Now see, force will be due to surface tension. Now can you tell me what is the formula for surface tension again? Yes, Hishma, you tell me what was the formula for surface tension?
S is equal to F by L.
S is equal to F by L. This means surface tension is the force per unit length acting. Yes or no? Okay, tell me what is the length of the film over here? Length of film. Yes, Aisha, you tell me. What according to you should be the length of the film over here? See, R is the radius. R is the radius. This is the wiring, which will be having the liquid. So what should be the length now? See, have you seen the bubbles that we used to play? You take this spherical portion, the circular portion, and you dip it in the liquid. Then what will happen? The whole liquid film will be over here. So length should be the perimeter of it. So now can you tell me if I say R is the radius, let's say, what should be the length of the film?
It
See,
should be 2 pi r.
2 pi r. Yes, it should be 2 pi r. Correct. Should be 2 pi r because r is the radius and this is the length of the film. Now see, since it is a film, it means soap film is there. So we have to double the length. So it means the length of the film would not only be 2 pi r, it would be 2 pi r multiplied by 2. All right. So now the force is equal to mg divided by 2 multiplied by 2 pi r, 2 times the perimeter of the circle. So now you have to substitute the values in this. Surface tension would now be equal to, what is the mass given? 3.03 gram. So we will convert it into kgs. Acceleration due to gravity is 10 divided by 2 into 2. That's 4 multiplied by pi. It's 3.14 multiplied by the radius. Radius is 3 centimeters. That is 3 into 10 to the power minus 2. This is Newton per meter. Just note this down.
Done, ma'am.
Now see, what is surface energy? So we have seen that surface tension is force per unit length needed to hold the liquid surface together. Now see, in order to increase the surface area of the liquid, work will have to be done against the force of tension. So this work done is in the surface layer of the liquid in the form of potential energy. Is in the form of potential energy. So the liquid surface has now more surface energy due to increased surface area. So work done against the force of surface tension to increase unit surface area is called surface energy. Or you can say the work done against the force of surface tension per unit area in increasing the surface area of a liquid at constant temperature is called surface energy of the liquid. This is also known as the free surface energy because mechanical work done can be released when the surface contracts. So what is surface energy? The work done to increase the surface area is stored in the form of potential energy, and the liquid surface has now more surface energy due to increased surface area. And this work done against the surface tension force to increase unit surface area is known as the surface energy. So the formula of surface energy is work done in increasing the surface area, work done in increasing the surface area in increasing the and increase in the surface area. All right, so increase in surface area, whatever is the work done and the increase in the surface area. That is known as surface energy. So let's see what is the relation between surface tension and surface energy. So it says consider a soap film having length of free surface L. Means if this is the length of the free surface, then length will be L. Now see, surface tension is the force acting. Surface tension is the force acting. So force due to surface tension. What is the force due to surface tension? We can simply multiply surface tension with its length, twice the length. Now we have considered a soap film. We have considered a soap film. So the length, as I've told you, the length will double because it has two areas, forward and the backward. So that's why the force due to surface tension would be S by 2L. This is like this. S was F by 2L. So force would be surface area multiplied by the twice of length. So this is the force due to surface tension. Now external force on soap film. Whatever the external force that will be acting on the soap film, that will be equal to this. So you can simply write it as if external force is negative of this force of surface tension. Now see, due to external force for soap film, displacement occurs by delta x. Means because of this external force, this will pull it apart. Let's say till here the L length has reached. So let's say this portion that has been extended is delta x. This is the displacement. Why? Because of this external force for the soap film displaces by delta x. Now see, if F external is the force and delta x is the displacement, what should be the work done? Yes, what is the formula for work done?
Force into displacement.
Force into displacement. So work done or by external force becomes external force multiplied by the displacement. So if you put it in the formula, work done by external, what is the force, external force we have calculated? That is surface tension into 2 times the length multiplied by the change delta x. Now see, work done by external, you can say, what is L into x? Length into breadth. Does it give the area?
Yes, ma'am.
It gives the area. If you multiply this 2 times length into breadth, that gives us the area. So this whole is the area. So you can say surface tension multiplied by the increase in area is the work done. A is the increase in area. Understood the formula for surface tension and surface energy? Work done is actually equal to the product of surface tension and the increase in area. Just write it from here.
Ma'am, can you scroll down? Done, ma'am.
Both of you? Aisha?
Yes, ma'am.
Okay, fine. Try this question. You have to calculate work done in blowing a soap bubble from radius of 2 centimeter to 3 centimeter. So if the surface tension is given to you, you have to find out the work done. Since the surface tension is also given in CGS unit and the radius is also given in CGS unit, centimeter is given. Find out the work done in ergo only. Don't convert them into SI unit. First, calculate the change in area. Radii are provided to you. Calculate the change in area. And then multiply it with surface tension. That will give you the work done. Aisha, any answer from your side?
Ma'am, I'm doing it.
See, first, let us calculate what is the increase in area coming. So increase in area means the change in area, final area minus the initial area. Soap bubble is given to us. What should be the surface area formula? Yes, Hishma, which formula did you use for calculation of the surface area?
F by L.
F by L. What is the force? What is the length? See, work done is
Ma'am,
given
in area 2 pi r.
not 2 pi r. See, 2 pi r is the perimeter. Perimeter of a circle is 2 pi r. Increase in area of a soap bubbles. Soap bubbles are spherical. Soap bubbles are spherical. Understood? So area for a sphere, surface area for a sphere is given by 4 pi r square. That is the surface area for a sphere. So see, how will we calculate? We have to find out the work done. Work done is given by surface area multiplied by the change in area. So we already have the surface tension with us. Now we have to find the increase in area. Work done is surface tension multiplied by change in area. Since radius is provided to us, we can easily find out the surface area as well, increase in area. So if we get the area, we have the surface tension. We can simply multiply these two and get the work done. See, how will we be calculating change in area? Since it is a soap film, it will be having two surfaces. So let us double it, twice the change in area. So 2 times, if this is the, let's say this is R1 is 2 centimeter and R2 is the final radius, that is 3 centimeter. Okay, Aisha, you tell me, if 4 pi r square is the surface area of a sphere, what should be the final surface area of this particular soap bubble? Four pi r square is the surface area of a sphere. R1 is the initial radius, R2 is the final radius. Soap bubble final radius is 3 centimeter, initial is 2 centimeter. How can we calculate the surface area, final surface area?
We need to find the difference.
We need to find the difference. Exactly. We need to find the difference between the final surface area and the initial surface area. Final area minus initial area. See, final radius is R2. So final area of the surface area of the square would be 4 pi R2 square minus initial area. Initial radius is R1. So initial surface area would be 4 pi R1 square. So if we take 4 pi common, we'll be left with 2 into 4 pi r2 square minus r1 square. And 2 into 4 pi gives us 8 pi. What is r2? R2 is 3, means 3 square minus what is r1? 2, 2 square. So this gives us 8 pi multiplied by 9 minus 4, that is 5. So 5 multiplied by 8 gives us 40 pi centimeter square. This is the change in area. Now see, now try. Now you have the change in surface area with you. You have the surface tension with you. Now tell me what is the work done coming. Note this portion and let me know what is your work done coming. Both of you, try it again. So the work done would be surface tension multiplied by area. That is 40 pi multiplied by 30, which gives us 1200 pi erg. So that is approximately, your answer is right, Aisha. 3771.3. It will come out approximately like that. Written?
Yes, ma'am.
Try another concept question based on this concept only. You have to find out the velocity acquired by the bigger drop. I'll give you a hint. Do one thing. Find out the work done the way we have been doing. Then equate it with kinetic energy. And since kinetic energy is given by half mv square, velocity you can find out from there. Equate work done with kinetic energy. From here you will be getting velocity. Just try this question.
Ma'am.
Yes.
Ma'am, is A the number of droplets?
No, forms a single drop. Means a number of little drops of water of surface tension sigma, all of the radius small r. If these are the small drops with radius small r. They are coalesce and they're combined to form a single drop. One single drop of radius capital R. Now the energy release means whatever work has been done in this process is converted into kinetic energy. Take n as the number of these drops. To get the relation between the small radius and the capital radius, you can do one thing. See, the volume will remain same. The volume of all these drops will be equal to the volume of this one big sphere. So you can equate the volume of both of these. You can take the volume of these small spheres and you can equate them with the volume of this bigger sphere. See, this volume of a sphere is given by 4 by 3 pi r cube. So if n is the total number of the small spheres, so that will be equal to n times the volume of each of these small spheres. That is 4 by 3 pi small r cube. That would be equal to this volume of the bigger sphere, 4 by 3 pi capital R cube. From here, you can get the relation between small n, small r, and capital R. See, 4 by 3 pi will get this cancelled by this 4 by 3. From here, you can say capital R cube is divided by small r cube will give us value of small n. Now see, if we have to find out the change in area, so what we can do is n times 4 pi r square means the area of this minus 4 pi capital R square, the area of this, surface area of this. This will give us the change in surface area. Now see, we already have a relation between capital R and small r. So if you place this in this, it would be 4 pi, you can take it as common. Now what will be left with? N r square, this small n and r square minus. From here, 4 pi has been taken common, so capital R square will be left. So this is the change in surface area. Now see, since n is not mentioned in the question, the number of droplets have not been mentioned in the question. So we have considered n from our side. So we have to eliminate this n. Since we already have a relation, let's put it in place of this n. So that will give us the change in area would be equal to, instead of small n, we can write capital R cube by small r cube multiplied by r square minus capital R square. So square would get cancelled by this cube and we'll be left with 4 pi capital R cube by small r minus r square. This is the change in surface area. Is this clear? Is the question clear till here?
Yes, ma'am.
All right, now see. Surface tension has already been given to us. Not the numerical value, but it has said that sigma is the surface tension. So now we have surface tension, we have change in area. We can easily get the work done. What is the work done? Work done is surface tension multiplied by the change in area. So surface tension is sigma and the change in area is 4 pi r cube by r small r minus r square. So this gives us work done. Now see, this work done is getting converted into kinetic energy. And the formula for kinetic energy is half mv square. So it means half mv square is actually equal to this whole term. So half mv square is equal to all this term. 4 pi sigma r cube by small r minus r square. This is the work done and this is the kinetic energy. Is it clear till here? Is this much clear? How have we reached till here? All right, now see. Now see, we have to find out this velocity. Velocity will be given, you can multiply this 2 with 2 pi, this 4 pi. So that will give us 8 pi sigma r cube by small r minus r square. This is the change in the radius. Now this mass will get divided and square, it would be replaced by an under root sign, means to the power half. Now see, m is also not given to us. If you carefully look in the question, mass is not given to you. It says number of little droplets of water surface tension sigma combined to form a single drop of radius capital R and energy is converted. It means there is no mention of mass. So we have to eliminate the mass also. Density is given by mass by volume. So if we want to eliminate the density mass, we can simply multiply density with volume. Understood? So let's write V equal to under root 8 pi sigma r cube by small r minus r square. So if the question is given in form of rho, if rho is mentioned to you, if the density is mentioned to you, you can eliminate mass. If mass is given to you, you can write it till here only. So it would be rho and volume would be again 4 by 3 pi r cube. Pi will get cancelled, 3 would be multiplied. So velocity, the final velocity that we have to calculate would be 6 sigma, this r cube is left, rho r cube by small r minus r square under root. Now in whichever form the option has been given, you can select out your answer. This much portion is clear? Is this question clear to you?
Yes, ma'am.
You start writing down the steps from here. And in between, if you have any doubt, you can ask me.
scroll down. Ma'am, can you scroll down? Done, ma'am.
Aisha, have you also written?
Yes, ma'am.
Okay. Now see, in this question, n was unknown to us. We didn't know what was the number of small spheres that were involved. Now let's see if number is given to us. I'm writing down a question. Just note it down and try it yourself. Do it similarly we did the previous question. Here, the bigger drop is being split into tiny drops, 27 tiny drops. You have to find the resultant change in energy. And if surface tension S is given to you, if surface tension S is given to you, you can find out the change in area. Change in area and surface tension will help us to give the work done, and that work done is the change in energy. Do it similarly. Start with the first step that we did in the previous question. Volume of big drop will be equal to 27 times the volume of small drop. Then try to find out the relation between the diameter and the radius of the small drop. See, in this question also, volume of the bigger drop will be equal to the number of times, n times the volume of small drop. And what is n given to us? 27. So it means 27 times the volume of that single drop, small drop. If this big drop has been split into 27 small drops, then the volume of these 27 small drops will be equal to the volume of the bigger drop. And the diameter is given d. So what should be the radius? If diameter is d, what should be the radius?
D by 2.
D by 2. Radius of the bigger drop is d by 2. Now tell me. Okay, Aisha, you tell me, what is the volume of bigger drop? Radius is d by 2. Radius is d by 2. What should be the volume of this sphere? It's a sphere. What should be the volume of this sphere? Yes, Aisha. Any idea?
D by, I'm not sure.
See, 4 by 3 pi r cube. 4 by 3 pi r cube is the volume of a sphere. Understood? So if d by 2 is the radius for this sphere, so the volume will be 4 by 3 d by 2 whole cube. 4 by 3 pi r cube is the volume of a sphere. where r is the radius. So volume of bigger drop should be 4 by 3 pi r cube. And what is the radius for the bigger drop? It's d by 2 whole cube multiplied by 27. Let's say the radius of smaller drop is r, small r. Small r is the radius of the small drop. So volume of the small sphere will be 4 by 3 pi small r. Is this step clear? D is the diameter of bigger drop and small r is the radius of the smaller drop. Now see, we can easily cancel 4 by 3 pi by 4 by 3 pi from here. Now what are we left with? D by 2 whole cube. Let's take the cube root. So it would be D by 2 from here. And cube root of 27 is 3. And r cube's cube root is 2. So r would be equal to d by 6. Is this clear? How did we get the relation between small r and the diameter?
Yes, ma'am.
Okay, now we have to find out change in energy. The question was asking us change in energy. So energy would be simply the work done, that is given by surface tension multiplied by the change in surface area. So if we have to find out the change in energy, that will be equal to surface tension. S is already given to us, surface tension is given to us, multiplied by the change in area. So 27 times 4 by the r cube. R cube means the small r cube. So r cube is equal to d by 6 whole square. Sorry, d by 2 whole square. Minus the area of surface area of the bigger drop, 4 pi d by 2 whole square. This is the work done formula. 27 times the surface area of the smaller sphere minus the surface area of the bigger sphere. Is this clear?
Yes, ma'am.
Okay, so see, so change in energy would be surface area multiply. You can take 4 pi common again. Now what are we left with? 27 into d square divided by 36 minus 4 pi has been taken common. So here it would be d square divided by 4. So it would be 3 multiplied by 3, 9, 3 and 9 multiplied by 4. So change in energy is 4 pi s from here. And what are we left with? 3d square minus d square divided by 4. So 4 will get cancelled. What is left? The change in energy is equal to 3d square minus d square is 2d square. So 2d square pi s. This is the change in energy that we are getting. Understood? Or should I repeat?
Understood, ma'am.
Okay, fine. Start noting this from here. And in any step, if you get stuck, just ask me.
Ma'am, can you scroll down? Done, ma'am.
Both of you.